Hi, Geometry. I wanted to quickly go over Lesson 87A, which you had to provide a proof for the second part of Theorem 87.1, which is that the similar polygons have they have a related ratio. The ratio of their areas is also related. So you're given specifically this part of the proof. This is the book's explanation, and I think it kind of cuts off a lot of the steps. So it's not a very thorough proof to show you step by step. So I wanted to break that down a little better for you. So we're given that these two, sorry, I imported this in from Word, so some of the math equations are a little weird looking. So we had to prove that the area of these two triangles is equal to the square of the particular segments of the bases here is what they're wanting us to focus on. So I put step one, and I was doing a paragraph style proof, but I numbered each line so it's easier to determine to refer to each line. And you can ask questions about a line if you have any questions about that. So here we're given, by the definition of similar polygons, and anything in blue, I'm just helping you out with some notes where I referenced it or where we learned that. We know that each of these segments ratios are equal to each other. So that establishes that, and that angle P is congruent to angle W. So that's by the definition of similar polygons. And I added this. The book proof doesn't say that, but it's making us assume that these dashed lines are altitudes. So I just add in just to make it a little firmer that SQ and ZX are altitudes and are perpendicular to the base by the definition of the altitude of a triangle. Thus, that means that angle PSQ is congruent to angle WZX. So these two angles are congruent. Here, let me sketch in here. So this angle and this angle are congruent by the right angles theorem because right angles are congruent. So therefore, we can say that this triangle here is congruent to this triangle here by the angle-angle similarity postulate. We need to do this because we need to be able to prove that these heights or these altitudes here are also congruent. That's going to help us with the proof here. So by the definition of similar polygons, and this is related to line 2, but we're just doing it for these smaller triangles, each of the related segments are ratios are equal to each other. So, and I was a little more detailed here. So since PQWX, which is right here, is equal to PRWY in this triangle, and then we know that the exact same segment here, PQWX, is also congruent to or equal to this ratio, then we can substitute that PRXY is going to be equal to QSXZ by substitution. We're going to need this for the remainder of our proof. So now we're going to state that the formula of a triangle is base times height divided by 2. Thus, and I added this step into, this is an extra step from the book proof, that you're going to multiply. These are just the base and height, the base and altitude segments divided by 2 of this triangle, and the base and altitude segments divided by 2 of this triangle. So then, using what we had to prove here, I substituted in what they were, and I wanted to just show that this is by division of fractions. So we have a fraction over a fraction, and we're dividing. Well, that's keep, flip, change. These cancel, and by simplification, we're left with this. And then I split them by, let me go back here so I can scroll. I split these two by multiplication just to show what I did here, and then I substituted, and this is back from this line, this in, okay? Because that then gives me, what I need here is that PR times PR is PR squared, and WY times WY is WY squared by multiplication. So then I can take from line 9 the area, and I've proven each step equal, that they actually are indeed equal to PR squared over WY squared, okay? So if two similar figures have a scale factor of AB, then the ratio of their areas is A squared over B squared. So you need to work the proof. I started working this kind of backwards. So I took this, the proof, and began working